So, in the previous lecture we were discussing the problem of repairing a machine that could be in two possible states, and we were getting information about that machine through inspections, and we had to decide whether we want to continue operating the machine or to stop and inspect it thoroughly, get the correct state of the machine and repair it if it is broken. Alright. So, what we will now do is decide what we will now do is model this problem as a stochastic control problem with imperfect state information. So, you can see it already fits in that particular framework quite well. So, the first thing to note is that we can to do this model as a imperfect state information stochastic control problem. So, let us write out this model. So, first is let us begin with the state. What should we take as the state of the system? So, it is natural here in this case the state of the system is the one that decides the cost that we will incur. So, the state of the system is really the state of the machine. So, the state of the system can be either P or P bar. We can take two possible actions, the actions, the control space. There are two possible actions, they have already been specified for us, which is to continue or to stop and repair, that is these are the two actions C and S. Now, the system evolution can be described in a certain way. Let us try to think of how the system actually was. So, for that let us go back to this particular figure that we had. So, if we are in state P here, and if we decide that if we decide to continue, then we would transition with then the machine just simply continues to run, and we transition from this state P to the state P bar with probability 1/3, or we remain in state P with probability 2/3. So, which means if we continue to run the machine, that means if we choose action C, then this particular transition here applies. Similarly, if we are in state P bar and we continue to run the machine, then this transition applies, means you transition from P bar to P bar with probability 1. So, let us write that down. So, the way to model this is to do the following. Let us write this state equation as follows. So, we write the state at time k plus 1 as equal to Wk, where Wk is a random variable. Really it is just a placeholder for us to describe that particular probability, the probability distribution shown in that or the transition probability shown in that diagram. So, here I will write that probability of Wk equals P is simply given xk equals P, and the action at time k is continue. So, if you took an action continue at time k when you were in state P, then you remain in state P with probability 2/3. So, that is really the probability of Wk taking value P given all of this, right. So, this is 2/3. So, this whereas you transition to state P bar under the same conditions with probability 1/3. Now why did I introduce Wk here? Why did not I write just the xk plus 1 directly out here? The reason is because I wanted to write out explicitly a state equation or the state dynamic. Okay, so these are my state dynamics now. So you can see they are kind of trivially written here. The state dynamics xk plus 1 equals the noise, where the or wk and the noise has this particular distribution. Wk equals p given xk equals p and uk equals c with a certain probability and so on. So the distribution that is written out here. We can write out something similar when we start off in state p bar. So if we start off in state p bar, the probability of that wk turns out is p, that probability is if we start off in state p bar and we continue. So you write uk equal to c, this probability of transitioning from p bar to p, that means the machine that transitions from bad state to good state, this we have been told is this probability is 0, and the other probability, which is that the machine remains in bad state, this probability is equal to 1. So far we have written the transition probabilities for when the action of continuing is chosen. Now let us write out the transition probabilities for the action of stopping and repairing. Now in order to do this, we need to understand very carefully what we mean by the state at the state xk. The state xk here is the state xk is the state at the beginning of time period k. So here is time period k, okay. So here is say time 0, this is at the beginning of the problem, this is at if time here we have time 1, then we have time 1, then we have time 2 and so on. So what we have is the state at the beginning of the time period. So xk here, when I write k here, so xk here will denote the state at the beginning of period k. Okay. So now with this understanding, let us write this probability carefully. What is the probability that wk is equal to p given that xk is equal to p and you take an action to stop and repair? Now which means that at the beginning of time period k, okay, you were in state p, you chose to stop and repair at that time. Now since you are in state p, the stop and repair operation has no effect, it will only keep you in state p. The next time step you will land up in state p based on the same probability that you have in this particular figure here. Okay. So you land up in state p, so it is like transitioning, you would be running the machine now for one period and you would land up again in state p with probability 2/3. So this probability here is also going to be 2/3. And similarly, if you talk of what is the probability of landing in state p bar, which means after one run of the machine, what is the probability that the machine goes into the bad state, that probability is again the same as given in the previous, in that figure here, which is equal to, which would be 1/3. So you can see these two are basically, these two probabilities are the same, and that is because continuing or stopping and repairing has no effect when you are in when the state of the machine is p. Okay, that means when you are actually in a good state. The repair action has an effect when you are in the bad state. So let us write that down now. So here now is the probability that you transition to a good state from a bad state when you take the repair and stop and repair action. So, you take a stop and repair action at the beginning of time period k, okay, with when you are in the bad state p bar. So, this now puts the machine back in state p. So, as I had said here, so this here the action, there are two possible actions. The first was to continue, the second was to stop the machine, determine the state through an accurate diagnosis, and if it is in state p bar, bring it back to state p. Okay. So, this all of this happens in, let us say, instantaneously, okay, at the beginning of the time period. Or immediately. So, in other words, we are ignoring the time that is elapsed in during which this particular repair happens. So, then in that case what happens is, it is as if you are beginning from state p itself, and then you would transition from state p, it is as if you are beginning here instead of here. So, although you were here, the repair operation has now taken you from here to here, and now one more round of running the machine will either take you to p with probability 2/3 or to state p bar with probability 1/3. So, this here is equal to, so this is the probability of going to p that will happen now with probability 2/3, and the probability of again becoming broke happens with probability happens with probability 1/3. So, you can see once again this is these two probabilities, in fact this and this, all three of them are identical, and with good reason, as I have just explained. Now, let us suppose since we do not know the initial state, we will be assuming that we have a probability distribution for the initial state, or equivalently we have a noisy observation of the initial state, alright. So, we will assume that the initial state is p with probability 2/3, and it is p bar with probability 1/3, alright. So, this is what we are going to assume this. Now, what are the observations that we get? So, we will denote the observations, the observation equation, or in this as follows. So, observations will be denoted like this. Observations Zk equal to Vk, and this will be, since we are doing this, remember we are doing these observations, we will be getting these observations at the beginning of the first two time periods. So, at time period k equal to 0 and at k equal to 1. So, we get, remember again, the probability of Vk being good, that means so the observations here are the result of the inspections. So, the observations here are results of the inspections that we get. So, going back to this figure here, we have a state transition. Now, at the beginning of the first two periods, we are going to get the results of these inspections, which is going to be these good or bad. The inspections are going to be noisy, so you may or may not be able to conclude the true state of the machine, but they do not tell you but if you do not know the true state of the machine unless you decide to stop and inspect after getting these observations. So, these are the result of these inspections are simply the observations that we are getting as part of the problem. So, this can be captured by our observation equation Zk equal to Vk for k equal to 0 and 1. So, now let me write out the probabilities with which these Vk's occur. Vk here is good if assuming the state is also in, we are in a good state, this probability is 3 by 4. The probability that Vk is bad given this is 1/4, right. So, we get when the machine is in good condition, the inspection gives you an answer good with probability 3/4. Notice we have written that here, and bad with probability 1/4, right. That is all that has been written out here. And similarly we have here Vk equal to G given that the machine is in a bad state or improper state, that is equal to now 1/4, and this is now 3/4. Now let us finally let us write out the costs that we will incur. So, we have 2 time periods here, there is no terminal cost. We have 3 we have 3 time going from 0, 1 and 2, there is no terminal cost at time 2. So, all we have to do is we have to minimize the cost over these two periods. So, the cost that we incur is, let me write it as G of x0 u0, which is the one at k equal to 0, plus you have a G of x1 and u1. Okay. Now to write let us write these out more explicitly. What kind of a function is this G? G, notice that G, when you are in state, we have been told that if you are in a good state and you take an action and you decide to continue, that continuing is costless, right. If you are in a good state and you continue, we do not incur any cost. If you are in a, if at any time you decide to stop, then you incur stop and repair, then regardless of the state you incur a cost, you incur a unit cost. So, that means G of p comma s is equal to 1, which is also equal to G of p bar comma s. Now, if you are on the other hand, if you are in a bad state, and you decide to continue running the machine, then you incur a cost of 2 units, alright. So, as we had, if you recall what we had written here, so we have a cost of 2 units for starting the period in state P bar, and there is a cost of 0 if you start in P. That means if you run the machine in state P bar, you have a cost of 2 units. If you run the machine in state P, you incur a cost of 0. If at any time you stop and repair, then you have a cost, that means you choose an action S, that means you have a cost of 1, okay. That is the cost that you incur, alright. So, we therefore have these four terms that define now our cost. Let us now finally write out what is the information that we have at every time. So, information at time 0 is simply the first observation, that is Z0, okay. So, the information that we have at time 0 is Z0, and Z0, remember, can be given through these equations here, Okay. So, Zk is equal to Vk for k equal to 0 and 1. We can write, we can find the probability of Z0 through these equations here. Okay. So, information at time 0 is Z at time 0 is Z0. The information at time 1 is Z0, Z1 and U0. So, this is the information we have at time 1. So, this comprises of the observations, the inspection observations that we have, the 2 inspections, and this here is the action at time 0. This here is the inspection, the result of the first inspection. Right. So, what we want to do therefore is minimize this, minimize our total cost, which can be written out like this: G0 or G of, let us say x0 comma u0, but u0 is chosen as a function mu0 of I0 plus G1 of x1 comma mu1 of I1. And this expectation here is taken over x0, w0, w1, v0 and v1, and we are minimizing this over mu0 and mu1. Okay. So, our policy comprises of these 2 decision rules, mu0 and mu1. Right. So, what we will do in the next class is actually try to solve this out explicitly. We will actually substitute for different values of I0 and I1 and write out the dynamic programming equations and then compute what the optimal policy should be at for this particular problem.